Okay, good morning, everyone, and thank you for joining us. Today we're going to have three guests that are at the cutting edge of structural innovation. The building structural systems have a huge impact on some of the aspects most critical to development, from affordability, through construction and construction cost and speed, sustainability, durability, and of course, how the building looks and feels from inside and outside. So today we will have Julia from Cree, who will talk about Cree's hybrid timber system. Alberto, who will talk about Holdex concrete floor system. And Austin, who will talk about about the structural masonry approach that was developed in building culture. So we will start, and you can type your questions in the Q&A box, and we will try to have the speakers address them at the end. So please, Julia, the stage is yours.
Thank you. I'll share my screen. Can you see full screen?
Yes.
Yes.
Okay, awesome. So hi everyone from my end, from Austria. I'm super happy for the invitation to present our system to you today. And I structured my presentation in 4 parts. I would like to tell you a little bit about Cree's history, then present our system, 2 of our projects, and as a last point, some of our KPIs, because Nama asked me to say something about costs and also time schedule regarding our system. And then, as Nama already said, if you have any questions, just type it into the Q&A section, and I'm happy to answer everything at the end. So I'm a structural engineer and a senior structural consultant at Cree. All right. So for those of you who haven't heard anything about Cree yet, we are an international construction collective for regenerative building solutions. And I would like to explain the term construction collective in a bit more depth to you. So Cree's history started with an R&D project where we worked on the question how to build higher with regenerative materials, how to build more sustainable. After that research and development phase, we worked as a general contractor ourselves, built several buildings ourselves, and mastered the structure during that time. The first building that we built is the Life Cycle Tower. That's a building that you see on the right-hand side, and that's where I'm currently sitting. Our goal was always to make the entire construction industry more sustainable, to really have an impact on the entire industry. Now you can imagine that as one company in Western Austria, the influence is only so much. That's why I decided to change our strategy and to partner up with general contractors all around the world. That's the Construction Collective. In the meantime, we do not only collaborate with general contractors, but with designers, producers all over the world. And that scales differently than only one general contractor. So I wanted to show you this just to give you some insights on the companies that we're working together with. There is licensed partners. Those are usually the general contractors, products and service partners who deliver products for and services for our buildings, and also very important in the entire setup, our creators, designers, architects, and engineers who designed these buildings. All right, so far for Cree's history. Those are the two projects that I would like to show you today. The one on the left-hand side is the Edge Südkreuz in Berlin, and the one on the right-hand side, it's the Victoria Park, 1925 Victoria Park, which is going to be built in Toronto at the beginning of 2025. The project in Berlin is an office building, and the project in Toronto is a residential building. So how many elements do you need to build a building? At Cree, we have 4 key structural elements. Basically, the structure is a skeleton structure. So for the horizontal bracing, we need a core, which is usually a concrete core, but could equally be a steel core or with additional shear walls. Then the second structural key element is our glulam columns. And you do see in that little sketch that it's double glulam columns along the perimeter and single columns in the corners. Directly attached to the glulam columns, there are timber frame walls, which are non-load bearing. So there's complete design flexibility with the wall elements. The third structural key element is our middle girders, just in case the building layout requires greater building depth. We basically assemble the middle girders, which could be either out of steel or concrete. And the fourth structural key element is our timber concrete composite slabs. And you see it here, it's 4 glulam ribs and then a thin concrete layer on top. Our approach is not to use as much timber as possible in a building, but to use all materials at their best characteristics to build hybrid, to end up with the most resource efficient structure. And this one is one of our buildings, Handwerkerhaus in Bremen. In total, 3,700 square meter GFA. And this building was assembled in 10 days only. So we have a speed of 370 square meter per day. We had even more square meters per day in other buildings. So usually it's 400 to 500 square meter per day of weather-tight enclosed floor space with only 6 workers on construction site. So there's 1 crane operator and 5 more people just checking how these fully prefabricated elements come together. All right, let's look into the projects, starting with the Edge Südkreuz in Berlin. Some facts and figures. I'm German, so you'll get some facts and figures from me. It's an office building, 32,000 square meter. Cree system assembly time, what I just mentioned with the 10 days for the other project was 30 days for the one building and 85 days for the second building, MK1 and MK2. The one is 7 stories, the other one 8 stories. And this project won hell of a lot of prizes, DGNB Platinum, DGNB Diamond, WELL Core Gold, WELL Platinum, and is currently the most sustainable building in Germany. So this is how the project looks like. The upper one, the rectangular one, is the MK1. The lower one, the atrium building, is the MK2. So you can imagine that the upper one, the rectangular one, fits perfectly for a system like ours. The lower one as well. Even though there are these slight angles, we were perfectly able to fit our system into the building. It just leads to some irregular shaped buildings, some irregular shaped slab types, sorry. So that's the project during construction. And then I wanted to show you some specifics of the project. This is a photo of the rectangular building, the MK1, and I would like to wanted to show you that cantilevering corner, which we incorporated in that building, and then for the MK2, that sky lounge. What I wanted to show you with these two is that you can include some special designs in your buildings, even though it's a fully prefabricated system with a very regular grid. So for these two, we just incorporated some special steel structure. So this is the sky lounge from the inside and outside, which was timber structure. And this one is a look into the office building. So you see that regular grid of the double glulam columns on the outside, and then the double glulam ribs, which is this very typical Cree look. And then this one is a photo of the atrium in the MK2 with these tree structures. And then with the stairs, you get into every single story of the building. Okay, the second project I would like to show you today is the 1925 Victoria Park in Toronto. It's a mixed-use apartment residential building, 18,000 square meter in total, 168 family-oriented units and 12 floors above ground. By including our system, we were able to have 32% less embodied carbon compared to a conventional structure and 50% less operation repair costs. And whoever would like to know a bit more about the project, I put the project website there, 1925vicpark.com. Then rendering from the outside. So you see we incorporated a balcony structure, then these setbacks at the top. That's view from the other side. You see a lot of greenery incorporated in the building, and then also some hallway and the atrium in the center of the building. And then this one basically shows the schedule for the building, which is 10 weeks of on-site casting for concrete, and then 7 weeks of installation for the Cree system. And remember, it's 18,000 square meter for this very building, and it'll be assembled within 17 weeks total. And then one thing that I wanted to show you is this very comparison. So for Toronto, there's a TGS Tier 4 standard, Toronto Green Standard. And this very curve shows a standard building for a design and planning phase, cost and time, construction and assembly, cost and time, operation and maintenance phase, cost and time, and then the return of investment basically after 25 years. Compared to that building, which is a very high green standard building, curve for integration of a system like ours. So the design and planning phase is much shorter, much more intense in the beginning, because we include all the designers from the very beginning, but also have proven solutions that we were able to use whilst designing the building. Then a much shorter construction and assembly period, early move-in, and then much lower cost for operation and maintenance, then avoided replacement of the building, just because basically the interior is it's an entirely column-free space. So the design could be changed at the end of the first life of that building, ease of upgrade, and then also ease of disassembly, because our system can also be disassembled and the entire building elements, for example, the slabs, can be reused in another building. And we have done that already. Which leads to 10-year earlier return of investment for the building 1925 Victoria Park. Then the last part, mentioning some of our KPIs. So I've mentioned it already a couple of times, timeline. By integrating all the design traits at the very beginning, we have that very intense design phase. And then what's important with that one also to have some design freezes is not possible to change, or the later the changes, the more costly the change is. And we have the offsite production in parallel, the on-site installation. And with that, we're 20 to 50% faster. We can deliver the project 20 to 50% faster. And I put in an example on the left-hand side, student housing of 15,000 square meter in Italy. The timeline for the conventional concrete building would have been 24 months. Timeline with CRE is only 15 months, which leads to a reduction of 40% of the construction time. Then global warming potential, an example of a project in Portugal. Minus 59% of global warming potential with partial replacement of concrete with structured timber, less concrete in the foundations, less steel, and less energy and water consumption on construction site. KPI asset value, according to the US Green Building Council, a building like CRE has a higher value with an increasing number of building owners seeing a 10% or more increase in property value, 10% more increase in property value. And the last one regarding rental income, rents for LEED certified buildings are 5.6 higher than for non-certified buildings. And I could continue telling you more about these KPIs, but I'll finish here.
Perfect.
The last thing I wanted to show you is just selection of our buildings, just to show you how these buildings could look like and how much design can vary. All right, thank you for your attention.
Thank you very much, Julia. Alberto, if you could load your presentation, and just a reminder for everyone, if you can type your additional questions at the Q&A box. So, Alberto, the stage is yours. Oh, perfect. You need to share the specific deck. Great.
And I think you're still muted.
Do you hear me?
Yes.
Okay, I'm Alberto Alarcón. I'm director of Holdec. And basically, the problem is we have to build 230 billion of square meters of new structures from now to 2016. And we have to do it in the most efficient way. So our company has been developing molds to manufacture the most sustainable concrete structures that can be done. How we do it? Well, this is our two-way system. This is our one-way structural systems. made with concrete. Basically, we have adapted a minimum for the compression layer that is depends on fire and acoustic regulations, and we have separated the maximum distance, the joist, and this joist has some holes that allow to pass the services through them. So basically, with this solution, we can cover a range between 6 meters and 22 meters. So we can make any kind of building, housing, industrial, offices. We have developed different technologies like precast technologies, semi-precast technology, precast technology including timber for the compression layer, and our construction system can be used anywhere in the world. It uses conventional concrete, conventional steel, conventional man labor, and it fits with any industrial culture anywhere in the world. So we can work in Canada perfectly. We have worked already in the United States. We have worked already in Latin America and Europe. So we are open to work anywhere in the world. I'm going to begin with a building that is placed in Barcelona. It's an office building, and this building has a spans of 19 meters. You can see here a picture of the inside of the structure. It's a small tower, and we just here our molds. They were precast on site, and they were post-tension. So we got a consume of just 0.17 cubic meters per square meter. That is nothing for nearly 20 meters. And well, as you can see here in this picture, we cover the 90 meter spans, but at the same time, we can integrate the services inside the structure. So it allows you to save height in the building. It allows you, of course, to save concrete and steel, and it allows you to save suspended ceiling and other elements. At the end, well, you can see here in this picture, compared with a conventional solution, we can save around 20% of the total height of the building, just integrating the services within the structure. We, of course, so solution is lighter, around 50% lighter than the conventional slab. You can save on columns, and you can save on foundations. And if you save on concrete and steel and suspended ceilings and other elements, you are reducing the cost of the total cost of the building and the total cost of the structure, of course. You can reduce the cost of the structure around 50%, the cost of the structure around of the whole building around 20%, and you reduce all these elements, you reduce the embodied carbon. It can be around 40% in the total building. So whole deck is not just a structure; it means a lot for the whole building. You save height, you save suspended ceilings. You can reduce elements. You can increase the speed of construction. You have a big flexibility for designers. And basically, we talk about a concept that is Holdex Zero, where we integrate developers, designers, and all players to make to allow this objective that is not a structure but a building that is cheaper and more sustainable than any conventional building. We are working in this turnkey collaborative project. I'm going to talk about two samples. I'm going to talk about, well, 3 samples. I'm going to talk about a building that has been designed by BIS Structures and Badger Roads architects. Another building that it has been designed by Serrano Architects, and the promoters is Corient Runway and Roche Pharmaceutic, and the builders are Sasir and Eleanor of these samples. Well, another important thing to remember is that you can use the saving of 8 of your building as you want. So you can. These are different possibilities. You can reduce the 8 of the building. You can increase the free 8. You can use different philosophies. Another option is to activate to make thermal activation of the slab, where you can get half of the volume of the conventional slab and an increased surface. So it works very well for thermal activated system. If you compare with other conventional systems in concrete, of course, Holdec is the most efficient way to make a concrete structure. We have checked it in with different engineers, and it's impossible to make a lighter structure. If there is any structural engineer here, I can talk with anybody about this. It's impossible to make a more efficient structure in terms of material, following the regulations. But the solution is so effective that it can compete with steel in weight, and it can still compete even with the whole solution of, for example, a CLT solution. It can compete in embedded carbon. We are competing in some projects. So we began with this is the beginning of the company, is the two-way systems. And we have moved to the one-way system. This is another sample. This is a building in Elche, in Alicante. And here is very interesting because we make an core and shell concept that this is the building finish. You can see that there is nothing. There are no services. There is no any other element. And this is the building with the companies inside. And so you can see, as you can see here, it's a very cheap solution. It's all the services and structure is completely integrated. And well, you can see here with the whole building finish. You can see there are different solutions for service and structure integration. Different philosophies. It depends on the designer, the architect, or on the engineers. And well, this is another building where you can see that the services are completely integrated, but they add some additional suspended ceiling. This is the finished building without the suspended ceiling. And in this comparison, you can see that CLT and Holdec solution can be very competitive in carbon, in embodied carbon. And well, Holdec is compatible as well with low emissions concrete. And well, we are developing actually other different solutions with like these ones with flat beams, and well, you can see that the service integration is perfectly possible as well. we are developing housing. Well, Holdec is compatible with a lot of different geometries and systems. Well, thank you for your time. Our philosophy is more with less. Basically, our idea is that sustainability is related to optimization, to trying to avoid as many constructive elements, concrete, steel, and any other constructive element. Thank you.
Thank you, Alberto. Very interesting. So Austin, the stage is yours. We have a few questions already, so remember to type your questions in the Q&A box.
Alberto, I think you might have to stop sharing so I can share. Can y'all see my screen, or is it still Alberto's screen?
Not yet, just a moment. We'll try to solve it. Okay, so I moved it to your presentation, but yeah, Alberto, if you can unshare. But Austin, we are, I believe we are. I am seeing your screen, and
okay, good to go then. Good, we're good to go then, Misha, you said?
Yep, I see your presentation.
Yes, yeah.
Well, thank you for having me, and really interesting to see Julia's and Alberto's presentation. Really impressive stuff, and I'm actually working at a much smaller scale than them on smaller scale buildings, more residential, smaller commercial, and also at the scale of a neighborhood, but lots of interesting overlap here. And so I run a company called Building Culture, and we are a design and build company, and also do urban design, architecture, construction. And we really focus on traditional design and also traditional masonry construction. And so this picture you're seeing here is of the a home that we built before all the framing. All the brick goes up first, because this is basically old school structural masonry, brick masonry walls, where you see exposed brick on the inside, and then we come in and put in the floor system and the roof and the interior partition walls. And before I jump into a little bit more of what we've done, you know, the things that we're really focused on at Building Culture is, one, you know, we think about sustainability too. We really care about that, but a lot of that comes back to beauty. So things that are beautiful are taken care of and last longer. So we think and talk about that in all of our buildings. We're concerned with not just climate change, but also human health, you know, and that the interior air quality in so many of our buildings and the toxic materials, especially in the United States, is really poor. And so we think about that. And then in terms of sustainability, you know, we're not only thinking about carbon footprint and stuff like that. And frankly, I think about that less than I think about long-term durability and resilience. And I loved Julia's note of on her buildings, how it was, you know, 50% less maintenance cost. And that's a huge deal in terms of a building being able to last. And the last part about things lasting, not just for sustainability, but also for sense of identity. And you know, many people that are in other countries, maybe your buildings last longer than ours do in the US, but so much of what we build in the United States goes into the trash, into a landfill in 75, 80 years, especially our housing. Oh, my presentation's not skipping. Okay, so this is just a little bit more showing our work, and we're doing really bringing in natural elements, natural stone. We can do cool, iconic buildings too out of brick masonry. You can see these naturally locally quarried sandstone lintels and stone sills here, and really hearkening back to, you know, more traditional aesthetic. But it can also be updated and kind of new and fresh. And we applied a lime wash to this one here, and can build beautiful architectural pieces. I just love brick because it's the size of the human hand, and you're really sculpting when you're using it. And so it's both artistic and functional. Just some other thing, just showing some other. This is just a normal 2,000 square foot house. I don't know what that is in meters, but 2,000 square foot house, you know, more commercial building here, and another home over here. And so this is the interior, one of that house I just showed you, the interior of this house right here before. And this is just a 2,000 square foot house, 1,000 square foot each floor. So not super big, 3-bed, 2.5 bath. And it's almost a townhouse, even though they're separated, but this could be a townhouse. And we love putting this interior arch inside, one, to bring the masonry inside, one, to experience the architecture. And then two, it's a small house. So yes, it's an open floor plan, but it's also providing a transition between spaces. And of course, you just can't be, and this was actually reclaimed brick that we use, salvage brick, 100-year-old brick. And then this building is where we really started innovating on our insulation. And so I'm just going to show you a little wall section of our insulation where we're using 2 double wythe walls. So wythe just being 2 layers of brick. So you've got 2 wythes here and 2 wythes over here. In between, we've got mineral wool, which is it's rock and slag, which is byproducts of metal making. So it's kind of recycled material. And then why we like it is because it's inorganic. It's hydrophobic, meaning it's the opposite of a sponge. It doesn't absorb water. It lets water run through it. Also, it's vapor open, meaning water can move in and out, because these are really mass wall systems where the masonry carries water, the brick carries water, and then it distributes that water throughout the wall. And you don't want to seal off one side where it can't breathe, is what some people would say, but really let water vapor move in and out. So that's why we use this insulation. And these ties right here are basalt reinforced ties that we get out of the UK called Teplo ties. And they're structural. And they actually use just a single wythe of brick and a single wythe of brick. And when you connect those with these structural ties, it's kind of like standing and spreading your legs out, and somewhere to push on you. You're really, even though you don't have anything in between, the wider your legs are, the harder it is to push you over. So it's really making the building function together. And so we've got a lot more exploring to do here. You know, this was our second, we've got 2 buildings like this right now, and we've got a number coming up here soon. And then I'm actually going to share a little bit of stuff that's, not my work. Last summer, I was actually in Spain near Madrid. We went to Segovia for studying historic masonry structures. And we were learning some old school thin masonry tile vaulting. This is a completely unreinforced structure where we're standing is 1 inch, so about 3 centimeters. Just one single layer of these thin tiles. And the only reason we have this strap around is just because our buttressing isn't really anchored to the ground. And this could be laid incredibly quickly. Fast setting gypsum mortar. And this is really a continuation of Gaudi and Guastavino and things like that. And actually, speaking of Guastavino, it's someone I'm very interested in, and something that we at Building Culture will be exploring more and more. Like I said, we're really into urban design, architecture, construction, and I know certain engineering, but ultimately we want to bring engineering in-house and really start working on these more complex forms of tile vaulting. But what Guastavino was doing was amazing. He's a Spanish master builder, really, you know, an architect and builder and mason. And he emigrated to the United States in the 19th century, late 19th century. And this was his first project. These completely unreinforced, no steel. This is about 3 inches thick, 3 layers of these thin tiles, clay tiles. And you can see he started exploring domes. This is a really famous restaurant under the New York City subway station. Just once again, you got millions of people walking over this, no steel in this whatsoever. Getting really, this is the first subway station in New York, starting to play with, you know, different patterns and colors and really making it beautiful as also part of the structure. Just really, really incredible stuff. And I'll share this one. This is really interesting. This is St. John's in New York. It's the 4th largest cathedral in the world. And this dome in the middle here, he built that, his son, erected that in 15 weeks, and it is 130 feet diameter. So what is that? You know, like almost 45 meters or something. So Santa Maria del Fiore in Florence, the Duomo in Florence, I think it took 12 years or 15 years to build that dome, and it was barely any bigger. It was like 140 feet or 145 feet compared to this 130 feet. Once again, completely unreinforced. This was supposed to be a temporary structure, but he put this on 100 years ago, and it's still there. I can't remember if it's 3 or 5 inches thick. Just unbelievably efficient. And really, what he's doing is strength through geometry, getting the geometry right, and then letting the forces flow through that. And I'll show you this last one. This is a helical staircase at Carnegie Mellon University in the United States. And you can see the structure of the staircase right here. These three little tiles right here. That's it. Once again, no steel in here. This staircase has been here almost 100 years. And just really unbelievable work. This is not really allowed today by code because people don't, and I say there are some people out there that understand it, but in the mainstream engineering profession, it is not understood because everything is moved to tensile strength and steel. And so I think it's not about, for me, a lot of that was this from an old presentation, but tile vaulting is kind of dead in the United States. Yes, there's a few projects here and there, but it just kind of disappeared all of a sudden in the 1930s, 1940s. When the Guastavinos died. And one of the professors at MIT, John Oxendorf, he says, at a place like MIT, you could easily fall prey to the idea that we are at the pinnacle of all time, that we are at the height of technological achievement in the history of the world. That's probably true with respect to understanding the human brain, but there are also lost arts. They could do things that we are only beginning to understand and appreciate today. And one of those things, in my opinion, is this structural masonry, clay tile vaulting, really understanding geometry and being able to make hyper efficient structures. This is a brand new structure right here. Once again, completely unreinforced, using geometry, and look at what they're stacking on it, and it's able to hold. And that's what I think about a building culture. It's not, just being nostalgic and copying what happened in the past or building as the Romans built or something like that. But it's also not assuming everything new is better, and really that idea of blending the best of old and new. And these are new structures being built today that they're experimenting with. And I want to show you one more. This is a concrete floor system by Philip Block and Block Research Group out of Zurich. And this is the bottom of the floor system right here. And this is all concrete that's molded concrete that's then, this is 5 pieces that's then craned into place. And so, just like Alberto was talking about, the speed of what they're able to do is incredible. There's no embedded steel in here whatsoever. They use a little bit of tension ties, so it reduces the steel by about 90%. That steel is external, so it can be maintained. And it all works in compression. So there's curvature to all of this. It all works in compression rather than trying to make a masonry material work completely horizontally, which is not really intended to work. And you can see the connection here with the rib vaulting of, say, King's College and the UK. I mean, look at that kind of similarity of what they were doing. So they were doing this 500 years ago and then innovating on this today of using it with concrete, really efficient. And he's doing this in the real world now too. And not that we are doing this yet, but I hope in the coming years, 5-10 years, that we are able to bring this to the States and also be doing this. And that is all I've got. Thank you.
Perfect. Thank you, Austin. Okay, great. So I'll start to try to cover some of the questions that were asked. And to those who asked them, I'll be combining some of them to kind of be able to address as many of them as possible. So I think there was a question about that was for Alberto, but I think it would apply to all of you, both about sound resistance without adding ceiling and floor finishes, or let's say with the generally reduced mass of I think practical all the systems. You have how you address that, and maybe we'll start with that, and the next related question will be to fire rating.
Okay. The more.
Yes, sorry, Alberto. I think maybe like it's actually better if you can address both of them at once, for each of you. The most
the biggest problem is the fire resistant. Okay, so our compression layer has the thickness following the regulations. For example, for 2 hours, we use 120 centimeters. Sorry, 12 centimeter thickness. And with that thickness, you fulfill acoustic regulations as well. So the structure has enough weight to fulfill acoustic regulation. We have built more than 100,000 square meters with this solution already. And the good thing is that it fulfills all regulations in Europe and United States. We have built already in United States. They are more or less the same related to concrete. The regulations related to concrete are more or less the same worldwide. I don't know if I have answered the question.
Yes. Austin, maybe?
Okay.
Maybe it's a better question for Julia. I don't think I have a whole lot to add on like we do our floor systems quite a bit different. I didn't show that. But the masonry in terms of fire resistance is great.
Yeah.
So yeah, we design everything accordingly. So whatever acoustic requirements the project asks for, we design accordingly. The plane system as such, maybe just to give you some numbers. So usually we can maximum length for this slab would be 10, 11 meters or like 30 feet. And then for that, or for standard length of 8-9 meters, we would have concrete slab of 10 centimeters, so 4 or 5 inches. And then the glulam ribs, which already provides some airborne and footfall sound. But yeah, basically you definitely need some floor built up, which for an office, usually we use double floor system and then some carpet on top, and that's usually perfectly fine. For residential building would be with some screed on top. Yeah, and then regarding fire resistance, so we do have 2 fire certificates, one for 90 minutes fire resistance, the other one for 120 minutes fire resistance. Both these certificates use less or have lower concrete depth than what's asked by code. So what we usually do is we design according to what's requested by code. And then for Eurocode, for example, it'd be a 10 centimeter, 4-inch concrete slab depth for a 90 minutes fire resistance. And for 120 minutes fire resistance, it'd be 12 centimeter. Or 6-inch concrete slab depth. And then in regards to the timber, there is 2 methods. There is to calculate the fire resistance. There is a reduced cross-section method or reduced material properties method. So basically just the cross-section shrinks in case of fire, and we design everything accordingly. So no problem.
Okay, I have 2 questions. I'll combine them to Julia. Both of them are about your experience working in the Canadian market and specifically on Victoria Park. So I think it was one was more general about learning and challenges, and the other was how receptive were reviewers, clients, consultants to your systems?
Good question. So we currently have one project or one building in construction in Canada. It's in Vancouver. And that was quite the process, just because it's also located in an earthquake region. So we had to do some design adjustments to fit the system there, which was basically an on-site concrete topping. So we had semi-prefabricated timber concrete composite panels, which did not only result out of the earthquake impact, but also out of the size of the panel. So it's 10 by 32 feet, or 3 by 10 meter 50. And the panels were just too heavy to be lifted by the crane. So that's why it was a semi-prefabricated panel in the end. And then for Victoria Park, much smaller slabs, but everything went nicely and swiftly. We had great design teams that we worked together with, who were both, for both projects, very passionate about using the system, very open to using a new system. But also the project in Vancouver was the first of our projects in Northern America. So that went really great. And then, for example, for the Victoria Park project, it initially was planned with 11 stories, and then authorities even allowed for 12 stories for that building. So, yeah.
Thank you. I have maybe a follow-up or clarification question to Alberto about the acoustics. So I think there was interest in acoustic separation on the same floor, considering the especially in the more kind of linear type of ceilings, and I would add maybe like the general applicability to when you do residential building in terms of especially acoustic separation between units, how it works with the services you run there, and also generally about I would say flexibility in use if the ceiling geometry makes it can make it maybe hard to divide the spaces relatively freely.
Okay. Okay. We have done some housing already. We have done housing in America. We have done housing in Andorra and in Spain. And well, basically, when you talk about acoustic, you have the acoustic separation, that is the compression layer, that it depends on the weight of the structure, is on the code. So it's in Eurocode and ASTI, American ASTI regulation, and it depends on the weight of the structure, and it depends on the thickness. That's related to aerial sound. If you are related to impact, then it's like any conventional floor. You need a layer of acoustic for the impact of the people walking. If we talk about the walls between different apartments, you can use any conventional detail, and you can build the wall against the compression layer, or you can build the wall against the beam. And if you, with the compression layer, there's any problem, it's like any flat slab, and with the pins, you just close the windows with a layer. I think it's better if you write us to our company, and we can send you some details about that solution. But it's very conventional. It's like we are using conventional plaster solution and conventional timber solutions for the walls. So everything is very conventional. The only difference is that we save around 50% of the total concrete related compared with a flat slab.
Thank you. Yes, thank you, Alberto. I think we'll have a last question. By the way, I didn't convey it maybe, but like the questions were also kind of showed a lot of interest in the system and systems and a lot of excitement. So I think this one will be to Austin. I think because both Alberto and Julia discussed price comparisons a bit. So I think the question is trying to understand general price implications, especially as they may apply to like larger projects. But yeah, price implications of using structural masonry.
That's a pretty hard question to answer because there's a lot that goes into that. It's like, what are you comparing it to and what are you building? It's easy to say though. I mean, it's not going to be cheaper, you know. But part of it is, in the long run, it's a lot cheaper. With how long it lasts and the lower maintenance and durability. And there's a lot of you get some efficiencies of scale. If you're building a rectangle, you know, the bigger the building, the more efficiency you get with your exterior wall, and that, you know, a 10 by 100 rectangle is 1,000 square feet. And if you just make that 11 feet by 100, you know, you've added 100 square feet with only adding 2 linear feet of wall. So I think there's a lot of application on commercial buildings, but once again, we're really working the residential right now, and then small commercial. When I say small commercial, like 2, 3, 5,000 square foot buildings. So I don't know if it's really applicable to what you're asking. But if we're comparing apples to apples on higher end construction, it's maybe 15, 20% more right now.
Perfect. Very interesting. Thank you. We'll have a few more questions, but we'll be ending it in the interest of time. But I think you can write our speakers and discuss yourselves. Yeah. So thank you so much for coming. It was very interesting for me. And yeah, have a good day.
Thank you.
Thank you. You too. Bye.
Bye.
Thank you. Have